this lab, we're going to explore the nucleophilic substitution reaction, in particular the SN1 versus the SN2 reactions. We're going to analyze a bunch of halides and see whether they undergo SN1 reaction or SN2 reaction. The chemicals we're going to use are 2-chlorobutane, 2-bromobutane, 2-chloro-2-methylpropane, 1-chlorobutane, and bromobenzene. All right, these are going to be the substrates or the halides that we're going to use in the reaction. And the reaction conditions that we're going to use for the SN2 reaction, we are going to use sodium iodide solution in water, 18% sodium iodide solution. And for the SN1 conditions, we're going to use silver nitrate solution in water with a little bit of ethanol present in it. Okay, so here's how we're going to set up the experiment. We're going to need 5 test tubes, one for each substrate, and we're going to do it twice because we're going to do the SN1 conditions and the SN2 conditions. Now, a general rule of thumb in the laboratory is 20 drops equals 1 milliliter. So we need 0.1 milliliters of each substrate. So that's going to equal 2 drops. So we're not really using all that much of these halides in that reaction. So 2 drops of the halide, and we need 1 milliliter of the solution. So we're going to use 20 milliliters of that. So for the SN1, separate out all your materials into 2 drops into each container. Then 20 drops of the silver nitrate solution is going to go in for the SN1. And you're going to mark the time. The second you add it, you're marking the time and making observations on what's happened. You're looking for a solid to form in this reaction, and we'll see what those solids are when I go through the mechanism on the next couple of slides. All right. If no solid forms after about 5 minutes of reaction, you're going to warm up the solution in the bath. This mixing we're going to do with the finger flick method. I'll demonstrate how to do that, so we really don't have to go crazy putting in a stir bar or anything like that. All right, so we're collecting data on the time it takes to form a solid. So if it's good at the reaction, right, if it's good substrate for SN1 reaction, we should see the solid forming quickly. If it's not a good substrate for the SN1 reaction, it might not form at all, or it might form slowly. We might have to do more work to get it to happen. All right, so you're going to make notes. You're going to record your observations in your lab notebook. For the SN2 set, again, it's set up the same way. 20 drops of the 18 sodium iodide, 20 drops of the 18% sodium iodide solution, marking the time. You're looking for a solid formation again, so it should be obvious when something happens. If no solid forms after 5 minutes, we're going to warm it up. You're collecting data on the time it takes to get the solid, so make sure you're making careful observations with what's going on with these experiments. All right, so the mechanism for the SN1, I'm going to do a general mechanism, not one for each individual substrates. What I recommend you do is after you find out what substrate undergoes SN1 reaction the best, that's the one that you should demonstrate the SN1 mechanism for in your lab report using ChemDraw. But I'm just going to take some generic alkyl halide, a chloride, and we're going to react it with silver nitrate solution in water. And the product that we're going to get is the alcohol. And we're also going to get silver chloride, which will be a solid, as well as nitric acid as the byproduct. And this will be staying in solution. All right, so let's look at the mechanism for this reaction. So silver nitrate is an ionic compound. It's going to break up into silver ion and nitrate ion. And silver ion has an affinity for the halogen. So what's going to happen is this bond is going to break, and I'm going to form the carbocation. I'll circle the charges just for clarity. You should use that template in ChemDraw, the circle charge. And I'm going to make silver chloride, which is going to be a solid for this. This is a reversible reaction, but having the silver chloride precipitate out drives it in the forward direction. So once we have the carbocation, water comes along, acts as a nucleophile, and it attacks the carbocation. We wind up with this substrate as an intermediate, where we have protonated alcohol, and then another water molecule will act as a base and suck up that proton. And we wind up with the alcohol. This hydronium ion that we get as a byproduct is really just acid and water. And we always have the nitrate ion floating around that we had from the beginning with the silver nitrate solution. So that's the nitric acid that we wind up forming, the aqueous solution of nitric acid. All right, so that's the mechanism for the SN1. Things you should note about this mechanism, it's unimolecular. This starts off all by itself, right? Breaking this bond to form the carbocation is a one-step process, and then the alcohol, the water will attack to form the alcohol as a separate fast step of the reaction. So the slow step is the breaking of that carbon-chlorine bond. That's the unimolecular part of this reaction. Okay, the SN2 mechanism is different. I'll draw, again, a generic alkyl halide. I'll draw the chloride, and we're going to react with sodium iodide in water. Specifically, if you wanted to look it up, this reaction with sodium iodide and an alkyl halide is called the Finkelstein reaction. It's named after a chemist with the last name Finkelstein, and he was the first one to popularize this reaction. All right, so the SN2 substitution, nucleophilic, and the 2 stands for bimolecular. So this relies on 2 molecules coming together and colliding with each other. So sodium iodide is an ionic compound. That means there's I minus in solution, and we attack. This is the bimolecular part. And we wind up with the iodide forming, kicking the chloride ion out from that. So the chloride ion is our leaving group. This is a reversible reaction. I wind up with the chloride. And then the sodium, which is floating around, which we had in the beginning from the sodium iodide, reacts with the chloride in acetone as the solution, as the solvent. Sodium chloride is much less soluble than the sodium iodide is, so it doesn't break up in the ions, and it winds up forming a precipitate that we could observe in this reaction. So if you look at this, you might think, well, I have this reaction to where the halide gets displaced. The iodide displaces the halide. And you would think, well, why can't the reverse reaction take place? Why can't the chloride come and attack the iodide? The iodide should be a better leaving group, and then this should just go right back to product. In reality, this is happening, right? This is happening. The reason we're driving the reaction in the forward direction is twofold. We're following Le Chatelier's principle, all right? If you remember from General Chem, Le Chatelier's principle, any reaction under stress reacts to that stress. So what we're going to do is we're going to add a lot more sodium iodide. So we're going to have an excess of I minus floating around in there. That's going to facilitate the forward direction. The more of this reagent I have, it's going to attack the chloride. Even if I make the chloride in the presence of a lot of sodium iodide, that chloride's not going to be able to get in there and do the reaction. The other thing that's driving this reaction forward is we're forming sodium chloride as a solid. That's essentially taking the chloride ion out of solution, right? So it's not part of the reaction and it can't do the reverse reaction. So both of those things are pushing the reaction forward. All right, some safety issues that you need to worry about. Alkyl halides in general are nasty. You don't want to breathe them, you don't want to touch them, and they should never be open, those bottles, outside of the fume hood. All right, these things are irritating to your eyes, your skin, and your respiratory tract if you breathe them in, and you don't want to do that. There could also be effects on the nervous system if you inhale a lot of this, and we want to avoid that. Some of them smell really bad. The more volatile ones, the lower molecular weight ones are the worst, and a lot of these aren't all that big that we're using, so they're pretty nasty things. Keep everything in the fume hood. Silver nitrate, if you get that solution on your hands, it will turn your skin brown, and it will last for quite a while. So make sure you're wearing gloves. You don't want to touch any of that stuff and get it on you. Acetone is a flammable solvent, so we got to be cautious of that. Make sure that we don't have any fires. And remember, all these things are toxic materials. Nothing is going down the drain. We'll have a separate waste container for everything. All right, as for the report, I want you to look at the rubric that I posted to Canvas. That has all the parts and what we expect to see in the lab report. Also look at the textbook reading that I posted, and I strongly encourage you to read the textbook for this section for more information about the lab. There's a lot of good questions that the textbook has that you should be addressing in your lab report to explain why you got what you got. So the bottom line, what I want to see, are the results what you expected? So if yes, why? If no, why? And be very specific. So let's say, I'm just going to use A as an example. So substrate A was the fastest in SN1 reaction. Okay. Why was it the fastest in the SN1 reaction? Should it have been the fastest one? What makes a good substrate for the SN1 reaction? All right, so you should know something about this reaction from the lecture. In general, the more stable the carbocation, the easier it is to do the SN1 reaction. So the carbocation that we're generating in this reaction should be stable. In general, tertiary carbocations are the most stable carbocations. So if it's a tertiary carbocation and it reacts the fastest, that makes sense. Let's say you didn't get that to happen. Let's say one of the other substrates reacted faster. That would not be consistent with what we expect to see, and you should try to explain that and maybe even try to reproduce the experiment to make sure that you have the right structure with the compound. All right, so that's the kind of stuff that I'm looking for in the lab. I envision the lab portion of this. If it takes longer than a half an hour, I'll be really surprised from the whole class. Getting all your test tubes together is going to be and getting your material set up to do this should be the hardest part. The fact that we're measuring with drops should make this reaction go so much faster than any other lab. The weighing is not necessary. All right, so good luck, and hopefully we'll have a good and productive lab section.